Thank you very much, Robert, for that introduction. Thank you for the invitation. Thank you for the organizers for the invitation. It's a real delight to be here and to talk with all of you. I bring greetings from your fellow space exploration and Mars exploration advocates at the Planetary Society. I bring greetings from the large number of scientists, engineers, technologists, students, and others who are actively doing the exploration of Mars with robotics, with Opportunity and Curiosity still active. And I notice one of my colleagues here, Bill Farrand, in the audience. He lives here and works here in Boulder. He's on the Opportunity science team, so you have Martians among you, which is kind of fun. So I want to talk about what Opportunity and Curiosity are doing on Mars lately. And let's see, maybe I can get the lights down a little bit. That would be cool if that's possible. But if not, it's all right. And it's a story, of course, about two pretty amazing robot geologists. This happens to be Spirit, but Opportunity is identical. Relatively small golf cart size vehicle for remotely exploring Mars. And then this monster truck is Curiosity, a much larger vehicle for remote exploration of Mars. And one of the things that it's really important for all of us to remember, and I know that this audience knows this, but many public audiences don't realize it, that the robots are not exploring Mars. Okay, we don't turn a switch and have a robot go explore for us and tell us what it found. It's humans, it's people, scientists, engineers, students, sometimes the general public, who are involved in doing this exploration, exploring this place, figuring out what it's like, laying the groundwork for sending people there, using robots as our proxies, as our eyes, as our fingers, etc. in these environments. I like to show this one because it shows the evolution of Mars rovers. Oops, let me go back. It shows the evolution of Mars rovers from the Pathfinder Sojourner rover in '97, Mars Exploration Rover Spirit and Opportunity in 2004, and then Curiosity of Mars Science Laboratory in 2012. So you can extrapolate to, you know, some gigantic rover out here sometime in the 2020s, right? Optimus Prime or something would be out here. But they are getting bigger and more capable. Curiosity is more capable in terms of its science instrumentation than Opportunity, and I'll talk about some of the science work that both of them are doing. So Opportunity has a science payload that it carries on board. It's a little spacecraft, just like an orbiter or a flyby spacecraft. It just happens to be landed on a surface and driving around with wheels. It has a mast with the cameras that take all those beautiful pictures up here. The mast is 360 degrees, straight up, straight down. There's an arm with the kind of the degrees of freedom of a human arm, the ability to touch the surface, to drill or grind into the surface in this case, to make take microscopic images. And then because it's a spacecraft, it has to have power systems, solar panels, communication systems. It has a mobility system and all that, kind of the standard engineering systems that a spacecraft happens to have. So very capable payload, and at the time, of course, the most sophisticated science payload that had been sent to the surface. Curiosity has kind of upped the ante in terms of the science payload. It's a larger vehicle, so there's more mass, more volume, more power available for beefier science instruments. So some of the instrumentation is the same: color cameras, navigational cameras, but much of it is kind of beefed up. There's a bigger arm. The turret on the end of the arm of Curiosity is the size of the Sojourner rover. So really, it's a large amount of material out there, equipment that has imaging, microscopic imaging capability, elemental chemistry, and a drill. First time to be able to bring a drill to Mars. There's a laser instrument that vaporizes little bits of rock and measures the elemental chemistry. And then inside, what you can't see is occupying a significant amount of volume on the inside, next to the computers and the heaters and the communication system, electronics and all that, are two laboratories that can process samples that the drill collects. The drill can collect these samples, and then through this kind of a Rube Goldberg process of moving the arm around in a Tai Chi kind of maneuver, you can get that powder into the body of the rover and analyze it with an organic chemistry laboratory and a mineralogy laboratory. And so we've done some of that with this rover. And these are things that weren't just not possible to get that kind of fidelity of the mineralogy and or any kind of organic information from Opportunity. Opportunity and Spirit went to 2 different places. Spirit, his mission ended in 2010, is inside Gusev Crater. Opportunity is in Meridiani Planum. Gusev, there was a geology story about this ancient possible river, and the hypothesis that this was a crater lake at one time was explored, and we found evidence for hydrothermal deposits and other evidence that it may have been a habitable environment. In Meridiani, there's a large deposit of the mineral hematite that we could see from orbit. Very unique kind of material for Mars. On Earth, this kind of mineral deposit is often associated with liquid water. We found that it's probably the case in Meridiani as well, and that there was near-surface liquid water, probably acidic in that environment a long time ago. And as far as astrobiologists are concerned, it's likely it was also a potentially a habitable environment, more than potentially. Curiosity is in Gale Crater, another large impact crater about the same size as Gusev, 150 or so kilometers across. And the big difference between Gale and Gusev is that Gale has this big mound of sediments in the middle, and this isn't just the central peak of the crater. This is much more than that. It's sedimentary material and beautiful layered deposits. I'll show you some of the pictures from Curiosity. And from orbit, we've seen all around the base of this mountain, which is called Mount Sharp, we've seen evidence for different kinds of minerals like sulfates and clays. These are hydrated minerals. They form in the presence of liquid water. And the specific details of what minerals are there can tell us about the environment. So with Opportunity in Meridiani, we used the minerals to tell us it was likely an acidic environment. And if indeed we found evidence of clays with Curiosity, we'd learn something about perhaps it being more neutral pH. And that would make the astrobiologists happy as well. So we landed in this tiny little ellipse here, and we're making our way, as I'll show you in a bit, to the base of that mountain where these mineral deposits are located. So let me just start by giving you an update with what Opportunity is doing in Meridiani. And here's the sort of one-slide summary. Today is Sol 3400 of our 90-day mission on Mars. That's pretty, 3,400 sols, right? That's pretty cool. I think the taxpayers have gotten their money's worth out of that one. We landed up here in January 2004. This January will be our 10th anniversary of the landing. Traveled this red path across the plains from crater to crater to crater to big crater here. Total driving distance more than 38 kilometers now. So Opportunity recently set the single vehicle land distance record off Earth, beating one of the Lunicod rovers for total distance traversed. And we've been using craters as probes of the subsurface, and I'll talk about that more in a bit. And we're at this large crater Endeavour now because we saw evidence of clay minerals from the NASA orbital data that are taken that help support us. So I'll talk more about that as well. So we landed, and it'd be really nice to get the lights down if there's any way to get the lights lower. Anyone? Okay. We landed inside of a very small crater, a little smaller than this room, right, called Gale Crater. We saw this outcrop in here, and this was really pay dirt for the mission. We could see that it was loaded with sulfur and sulfate minerals, certain kinds of sulfate minerals, including jarosite, for example, that tell us that these are water-formed, hydrated materials, and they either formed in or were associated with a relatively acidic water. This is a very exciting thing to discover relatively quickly, but of course we had to ask ourselves, you know, what else is going on? And we looked at the surface and found these, spectacular mineral grains covering the ground, littering the ground, actually. And very difficult to study these because they're the size of BBs, a couple of millimeters in size, and the instruments are designed to measure kind of macroscopic things, not microscopic things. And so we had to find collections of them where they could gather together and we could make a differential measurement. And we saw that these are at least one of the materials that contain that hematite that we could see from orbit. And so one hypothesis, which is our favorite working model, is that these are a kind of geologic material called a concretion. They form in very porous, water-saturated rock as that water is slowly leaching away or evaporating away, almost like a stalactite or a stalagmite might form as water is dripping inside of a cave, releasing the minerals as they precipitate out of that water. And if everything is nice and smooth and even, that'll happen in a nice spherical fashion. So there are many examples of these in the desert Southwest, for example. And we think that's what these are, and that these and other features that we see in the landscape, ripple marks, certain kinds of cross beds and other mineral indicators, tell us that there was a lot of water here very close to the surface and that it was a habitable environment. Now, whether it was inhabited or not, that's another story. And Opportunity doesn't carry organic chemistry instruments, so it wasn't designed to be able to find evidence of life on Mars unless we happen to see a fossil or a little green thing get up and walk in front of the cameras. Then, okay, then we'd have the evidence. But that didn't happen. So that Eagle is where we landed, and we went to visit these other craters, Endurance and Victoria, because those are bigger holes in the ground. They're places where Mother Nature has dug up more of the subsurface and exposed more of the subsurface for us to view. And so we wanted to find out if that water we passed went even further back in time. And so here's Endurance Crater. And the cool thing about this is we actually got the rover drivers to take us down here and along these slopes. Very precarious driving, very risky situation for a vehicle that cannot be controlled in real time. There's a huge latency, 1 day latency at least, between telling it to do something and then seeing the results of that happen with the current way that these missions are done, and speed of light, which you can't change. So there, was a real achievement in an engineering sense to get them to drive up there. Here we are with our monster truck waiting to go down into the crater. We had to be careful in this and other craters because they often have sand dunes collected in their bottom. They're kind of like lobster traps for sand. The sand goes in and it can't get out. And if you look at Mars from orbit, you see these all over the place. And so we wanted to study them and get close, and we could get close and study them and take spectacular photographs, kind of Andy Warhol-ish with infrared filters. And this is kind of a compositional map where the brighter reds are more iron 3+ and the darker blues are more iron 2+ kinds of materials. But this is sort of as close as we could get because we knew if we drove into here, that would be the end of our mission. We would just slip slide away and never be able to get out of it. But we did get along that wall of the crater, as I mentioned. So this is that precarious situation of sitting at about a 25 degree tilt, looking over our shoulder, taking a 180 degree panorama, looking at these beautifully layered sandstones. They've been lithified. There's evidence of cross beds in here, kind of like you would find in an environment on the Earth where there were ancient sand dunes that had been compressed and lithified over time. And the difference here is that these are loaded with these little blueberries that it's been inundated with water, probably multiple times, with that water coming up to the surface and back down again. And we saw that those mineral and geology indicators of that water throughout this whole stack of many meters thick. Now, we don't know how old this is. We don't have age dating tools on Opportunity or Curiosity, by the way. Those tools, like radioactive dating, are still laboratory size, waiting for somebody to turn them into a shoebox to put on a rover. And there are people working on that. And so that's coming, but we're not there yet with that technology. But still, we can say in a relative sense, this stuff is older than that stuff, and this might be, ancient subsurface, and this is kind of jumbled up impact crater materials. We could do relative age dating and make some guesses about things. Now, when we're not in a crater, here's what the environment looks like in Meridiani Planum. Okay, it's not particularly exciting. It's a great place to study sand dunes and sand ripples. But even my colleagues on the team who study sand get kind of bored with these places. So it's kind of like driving from LA to Vegas, right? You just want to get through here, get to the other side as quickly as you can. And we actually got stuck several times, including at this location, by getting a little bit cocky about our driving and spinning our wheels into some of these ripples and getting stuck. So we had to be careful and learn how to drive in this environment. We got to Victoria Crater, and I put the rover in there in the computer. That's not the real rover, although we did have the vehicle up there at one point in time. But I put the rover in, or other things for scale, like all these Buzz Aldrins. You put them in here because there's nothing for scale on Mars. There's no trees, there's no houses, there's no abandoned shopping carts, there's no tumbleweeds. You know, we're so used to something for scale in our own landscape, a road, a distant tree, something, and it's just really difficult to tell that this is an incredibly precarious and steep cliff where, you know, if Buzz were there, he would only be that big, right? And so it was, again, a challenging drive situation. We had the rover, actually I think it was up here for a little while, very close to the edge, and I remember the day when the drivers were planning the backwards drive to leave that place, and there were like 7, 8 people, and an upper management came in. You guys, you sure you got the sign right? We're going backwards, right? Can you check that command again? That's a negative, right? Yeah, okay. And we backed away. And I actually showed this slide to Buzz, and he said, I don't remember that EVA. So I'll just flip through these. You know, this was a real postcard vacation at Victoria. All these spectacular exposed cliffs, and the people on the team who are doing stratigraphy were able to dive into this and map all these beautiful geologic units that go around the crater. This layer right here, for example, is hypothesized to perhaps be the ancient pre-impact surface before this giant crater was formed. Much of the crater has been eroded away. That's why it's sort of smooth around the outside. Well, we went from Victoria to Endeavour, an even larger crater. So you can see, you know, small crater, bigger still, probing deeper into the subsurface, deeper into the stratigraphy and perhaps the ancient past of the planet. And as I said, we were compelled to look especially at these places that we saw from orbit as having evidence of clay minerals. And we saw not only clays, but also sulfates, places on the ground where we could see these little veins. And this is only, you know, this is less than an inch or so thick. It's kind of like a small vein you'd see in a crack going on a hike in the mountains up here. Except when we put the instruments down on it, we see all kinds of calcium and sulfur. We can tell from other indicators that it's likely to be hydrated, and so that points to gypsum as the mineral, which is a very common vein-filling mineral in cracks and fractures on the Earth. And gypsum is dissolved in these fluids that are traveling through the rocks under pressure and infiltrating these cracks and precipitating out. We also saw some really interesting coatings on many of the rocks, and we think that these coatings may be at least one of the carriers of the clay minerals that we saw from orbit. But we don't have a good spectrometer or other instrument to actually measure the mineralogy of clays on this particular rover. So it's an inference. We put a bunch of pieces of the puzzle together, hypothesizing that the clays are a part of the story, the sulfates are a part of the story of groundwater here. And we actually have a paper that we submitted for peer review that's hopefully going to be reviewed and published soon, where we talk about these recent results. So Opportunity has been incredibly productive and still continues to be productive. We had to park last winter, our last 5th winter, on a sun-facing slope because the rover is solar powered. Solar panels are getting dusty over time. So unless we tilt into the sun, we don't get enough power on those panels. This rover is not as dusty as Spirit was. It was dust on the panels that ultimately killed Spirit by choking off the power that we needed to escape from the place we got stuck. Hasn't happened Opportunity yet, and we've been intentionally trying to find places when the sun is lowest in the winter to tilt and park into the sun. So we just finished our work at this place called Cape York, where those results will get published hopefully soon about the clays and the sulfates. We did this zip drive across Botany Bay here from May through October. I was really impressed at how quickly we made that drive to this second piece of the rim. These are pieces of the ancient rim of Endeavour. I mean, the second piece here also shows evidence for those clay mineral deposits, and we've just got there. So we're just starting to think about where to explore this area. Here's that piece of the rim here, and we have to go there for 2 reasons. The science is compelling. We see some mineral indicators of past habitability up there, but we also have to go up there soon at those angles because we've passed Mars summer, we're into Mars fall, Martian winter is coming, the sun is getting low, the panels are dusty, and these are the right angles to tilt into the sun like a lizard to let us survive this next winter. And we think that if we can get up here and the dust situation doesn't get worse, we might actually be able to drive around up there during the winter if we stay at that angle, kind of switchbacking at that angle, and do some science. So we're on our way up there. Here's a picture from yesterday, combination of a NavCam Mosaic and some PanCam pictures. I think we actually just parked by this rock relatively recently, looking for rocky targets and outcrop, places where we can use the instruments to test these hypotheses about ancient groundwater and the past mineral history. So, you know, opportunity is never in the news. It's old. It's, oh, is it still alive? It's still going. Oh my God, it's still going. It's still doing great science. It's doing great science on Mars every day, and a very devoted and dedicated team still working with that vehicle. All right, now what's going on with Curiosity on the other side of the planet? Landed inside Gale Crater, not exactly in the center of our planned ellipse, but just a little offset from it. And we're trying to get to the base of Mount Sharp, which is down here. It is day 367 of our 689 Mars Day primary mission. So we're almost, halfway through our primary mission, and we've done some pretty interesting stuff. When we landed here, you can see the dark stuff is from the scour marks from the retro rockets. Made it darker by cleaning off some of the dust. And we wanted to get to the base of Mount Sharp, so we instantly went the other way, right? And there were actually logical reasons to do that. One is that the geology really close, within 500 meters of where we landed, turned out to be extremely interesting. We could tell that from orbit. And it took this long and this much driving for the engineers to just check out all the equipment. It's such a complex vehicle, and the different systems, the mobility systems, communication systems, computing systems, and all the instruments, all those complex instruments, 10 to 11 payload pieces of the payload had to get checked out. So we did a little driving test to get out here, and then did some really interesting science when we got out there. You've all seen the pictures from the surface. Here's some of those scour marks from the retro rockets. Here's beautiful Mount Sharp, which looms in every single panorama that we take, kind of teasing us. We want to go there. That's our destination. That's our goal. And we drive and drive, and we don't seem to get any closer. You know, it's like walking around on the moon. There's not as much haze to give you a sense of distance. But we are getting closer, and I'll talk about that in a bit. One of the first discoveries we made, just very close to where we landed, were these beautiful kind of cemented, rounded pebble deposits, almost like you went in the backyard and decided, I'm gonna smash the little basketball court. I'm gonna break up that cement and take it out. This is conglomerate. We hypothesize it's conglomeratic material. The rounded pebbles are stream bed materials. That's our hypothesis. And it looks like, very much like these materials came down a channel on the wall of the crater down, and were dispersed out in a fan across what is now our landing site. Very good evidence for not just water near the surface, but rapidly flowing, relatively deep, knee-deep, ankle-deep water at the surface a long time ago. And again, we don't have age dating tools, so we have to go based on the broad Martian timescale to say that these are ancient, but we don't have absolute age dates for these. But it was a very interesting, relatively quick discovery that the mission made, that there are these rounded, cemented streambed materials. It took a while to check out the ARM instrument, so for a while the only way we could measure elemental chemistry was by using the laser, which isn't actually a visible wavelength laser. This is a dramatization, right? But it zaps a laser beam at the surface, and here's our first zap here. So that's also a dramatization. Okay, that's a joke from the PI of that team. Here's what it really does. It makes this tiny, tiny little zap hole, laser-induced breakdown spectroscopy it's called. It's used in archaeology and the art business all the time to measure the chemistry of paints and pigments and pottery and things like that, because it does so little damage. This is, a human hair-sized pit that forms in these materials. So you can, and it creates a little vapor cloud which emits a spectrum, which is then measured by the spectrometer. So it allowed us to get some details on the chemistry of these rocks. Many of them are what a geologist would call basaltic, just like you'd find in Hawaii or Iceland or parts of the desert Southwest. And it's a common material on Mars. Mars is a volcanic basaltic planet, at least in the most recent part of its history. We started doing things like digging into the sand, and we have a scooping device that brought some of that sand into the rover's instruments. This was an engineering test. Can we scoop materials? Can we dig into the surface with the wheels? Can we get those scooped materials in the arm, do the Tai Chi thing, get them into the instruments and measure their chemistry? And the folks who run these instruments really wanted to do that first test on something that they knew what the answer should be. And so this is just volcanic basaltic sand with olivines and pyroxenes and typical kinds of minerals you'd find in volcanic rocks even on the Earth, and that had been known to exist on Mars for some time. And they ran the whole system, got the material into the instrument, and got that answer. So that's good, right? It's kind of like having a control experiment. Not only did the engineers get the testing that they needed done to demonstrate that the system works, but scientifically, we validate something that we thought we knew, which is always good to do in case you didn't get the right answer. And secondly, we can have confidence that next time we put things we don't know into this system, that we can trust the answer. And so that's what we did down here. This area called Yellowknife Bay is a place where 3 different kinds of geologic materials come together very close to the landing site. This sort of hummocky plains that we landed in, this lower elevation cratered plains, and an even lower elevation fractured polygon fractured material that we saw. And in fact, this area right here is some of the lowest elevation anywhere on the crater floor. So if, for example, there was water there at one point in time, this would have been the last place that it was, the lowest point, the deepest point under the water if it was deep. So that compelled us to go there, and we found all kinds of interesting things, more mineral-filled veins, some observed at high resolution with the microscopic camera, which can also take wide-angle pictures. This is from the microscope, this image. It's a mosaic, actually, of many different images with the arm out like this, and kind of like, you can do with your iPhone, kind of, take a picture of yourself and kind of hold it around like this and make a mosaic. And you don't see the arm because the arm is behind the camera, right? And we saw all kinds of interesting veins, some of which appeared to be hydrated, most of which contain calcium and sulfur. So we're seeing the gypsum again, the groundwater evidence like we saw at Opportunity. And this was where we did our first drilling. First drill holes on Mars, first a mini drill test hole, and then the real deal, drilling into Mars about that deep. Okay, big deal though, right? I mean, that's the first time we've been able to get under the subsurface. And when we could grind into the surface, into rocks and other materials, outcrops, with Opportunity, we could clear the dust off, and sometimes most of the time, especially at Meridiani, we'd still see reddish material in there, that hematite kind of going through that entire grind distance, which is only less than a centimeter. Now going down 5 or 6 centimeters into the surface, it's not red Mars anymore, it's gray Mars, right? All this is very gray, much less oxidized, much more iron 2+ than iron 3+ material. And when we got those powders into the instrument, voila, this cornucopia of 20%, 30% abundance of clay minerals were discovered in these drill materials, just under the surface. So just below the surface, just below what is a dusty, oxidizing kind of material on the surface, appears to be a much less oxidizing environment containing water-bearing, water-formed minerals that had to have formed in fresh water, not acidic water. And this was just supposed to really be a test of the drilling at a place we could go nearby, and it turned out to be just a bonanza of scientific information that we weren't expecting to see here. The clays were supposed to be all at the base of Mount Sharp, not right where we landed. So again, sort of an early, exciting science return that happened to justify everybody was agonizing, oh, we're going to waste all this time by going the wrong direction. Well, we got there and found some really interesting scientific results that were not necessarily expected, but that have a lot of implications for Mars as a habitable world. Perhaps even more so than the acidic Mars that was found at Meridiani and arguably even in Gusev at home plate. This is more of a fresh Mars, freshwater kind of Mars. And so I know Carol Stoker's here, an astrobiologist. She's got to be excited about this at some level, right? Yes? Yes, okay. So talk to Carol all about it, I'm sure she'll tell you more. So I'm involved with the cameras, and here's our 2 color cameras. We have we have different focal lengths on the eyes. One is a wide angle, one's a narrow angle. It was supposed to be a zoom camera, but that was descoped by NASA headquarters on us. But we still use these systems every day to take beautiful color pictures and color panoramas. It has this sort of self-portrait kind of view has inspired some art. Here's kind of a curiosity Andy Warhol thing and American Gothic curiosity. There's opportunity there, It's kind of cool. But more importantly, we use the high-resolution camera, this telephoto lens. What would you do if you had a telephoto lens on Mars? Well, you'd take beautiful pictures with it, wouldn't you? Like the layers and the slopes of Mount Sharp. This is where we want to go. Geologists first saw these pictures. A very good friend of mine who's a field geologist, she cried, and we were all in tears when this picture came down. Seeing the level of detail in here, and you can zoom and zoom and zoom, and you can find these online very easily. Huge amount of detail in here, and they're starting to map these layers out, and there's obviously some big difference. Everything goes at this angle up here, and everything goes at this angle down here. There's an unconformity here, a geologist would call that. A change in the environment, a change in deposition or erosion. We're going to drive up into these slopes and look at these layers like reading the pages of a book. The history of the Earth is really figured out from going to places like the Grand Canyon, where you can see it all exposed in plan view and cross-section. And here's a place on Mars where we may have a very similar situation. That's why we chose it as a landing site. We want to go there, get there, drive up through these layers, and read the Geologic Book of this planet. This is a little accented, little harshly stretched in color. The real colors are more muted than this. But this is dark sand at the base of the mountain that we have to get through, and we found ways to drive through this, and these are the layers that we want to explore. I'll just add a couple of things recently, because there's probably some astronomers in the crowd, and there was just a talk about Phobos and Deimos. We can use that high-resolution camera to look up as well as down. So relatively early in the mission, we caught a really nice solar transit of Phobos, kind of a grazing transit, and you can see the outline of the shape of the little moon there. And these are really useful because, as the previous speaker mentioned, Phobos' orbit is slowly spiraling in. It's changing with time, and traditional astronomers haven't bothered monitoring the moons of Mars. It's not real astronomy, right? But when we first did this back with Spirit and Opportunity, Phobos was not where it was supposed to be because it's decelerating. And we're learning things about the interior of Phobos and perhaps even dissipation within the interior of Mars by doing this. And then just a couple of weeks ago, and this just came out on the web, we did this mutual event, Phobos eclipses Deimos. And Phobos is moving one way, Deimos is moving the other way, right? Phobos is orbiting Mars faster than Mars rotates, so it rises in the west and sets in the east, and you can actually see both of them moving relative to each other. And again, this is a beautiful way to get the exact contact point of each interaction in plan view, tells us about the orbit and allows us to refine the orbit to very, very nice and high accuracy. To get some more information about the history of these objects. So we can do astronomy from the surface of Mars too, which is kind of fun. Here we are at, today is Sol 367. As of our last drive, we'd gone about here on this scale, about 800 meters from where we did the drilling. The green dot is where we landed. The yellow star is where we are. That's where we want to go. So we still have 7.5 kilometers to go. We're trying to drive as much as we can every day. The rover drivers are implementing new software updates and trying to improve the capability to go more than 40, 50 meters, maybe 100 meters routinely, maybe more than that if we can bring in the high resolution data and get that stereo information in with them. But we're still talking many, many months to get down here. We're trying to drive as much as we can, but we're trying not to be irresponsible scientifically. We can't just put blinders on and drive past a dinosaur bone, right? We can't do that. We have not seen any dinosaur bones, but we're looking. So we have to be very careful about, trying to drive and balance that with, okay, let's do some limited amount of science here and here and here, and it's a balancing game right now to try to beat the clock and get to these juicy units by the end of the primary mission, or before the end of the primary mission, when our engineering friends tell us the warranty runs out, which is sometime in about June of 2014. So the clock is ticking on us, and we know kind of in the back of our minds that this is the same guys and gals that built Spirit and Opportunity, and you said they were going to last 90 days, right? Yeah. 689 days on Mars, yeah, that's when it's going to stop working, yeah. Well, who knows? You know, these are all risky things, and it's not clear whether we'll survive beyond that, so we're trying to do as much as we can. In the meantime, here's yesterday's drive direction Mosaic. Here's what we're looking at. Relatively smooth sailing, not a lot of obstacles in here, so in terrains like this, we hope to make a lot of progress, and not a lot of things to distract all the scientists. Oh, look at that, oh, look at that rock, you know. In terrains like this, it's easier to go far every day as opposed to showing up on an outcrop or with a beautiful set of layered rocks in front of us and that kind of thing. So this is my last slide. I'll just leave this up here with some nice websites. Hopefully you're all following along on the MSL website or the Mars Rovers website for Opportunity. We put the raw images, the JPEGs out there every day from all the cameras. Sometimes they're a day or two behind. It depends on the timing of the downlinks from the MRO and Odyssey orbiters. That third site is our PanCam website for the color images from Spirit and Opportunity. If you want to wallpaper your bathroom with Mars, that's where you get the 300 megabyte TIFF file. And then the Planetary Society has some wonderful blogs by Emily Lakdawala and by Sally Rail, for example, that keep us all up to date. Even those of us involved in the missions learn things from these blogs because they're interviewing people in many different parts of the mission. It's almost 500 science team members on Curiosity, for example, and it's really hard to keep up with what's going on. So whether it's general public, space enthusiast, or Mars rover driver, these are great ways to keep up with what's going on. And hopefully you will, and hopefully you'll believe that even though, yes, it is easy to be impatient, that these are stepping stones. These vehicles are providing basic information about the environment that people will go to. These are laying the groundwork for future human missions. The next Mars rover, launching in 2020, will hopefully cache samples that can be brought back in the 20s, hopefully, to tell us in detail what that environment is like and to cross off all those risk questions about, you know, oxidizers or other strange components in the Martian environment, study them in great detail, make sure we understand the best we can before people go there. And, you know, these vehicles are doing an enormous amount of work for maintaining public interest in Mars exploration. For many people, this is what NASA does. For many people, this is the most successful thing that NASA does, not the shuttle or the station, but these kinds of vehicles, and Cassini around Saturn, and Dawn at Vesta, and all the robotics. And they are providing, I think, an outstanding foundation if we can get our politicians, if we can get our national will to put the effort into it for eventually getting people on the red planet. So thank you again.
All right, we have a question over here.
Yes, sir.
Wonderful missions, so exciting. But I do think you missed this wonderful public relations opportunity after landing, and that was to go and take a real close look at the sky crane and the parachute, and I wonder why you didn't.
So yeah, I can address that directly. It was not a missed opportunity. It was an intentional avoidance. And that's because the team that put the organic chemistry instrument together, their investigation would have been over. The contamination in that environment is already known what materials are there, and there's probably like a cloud of material and, you know, material condensing on surfaces that's constantly breathing out in that environment. That would have severely contaminated the organic chemistry experiment. And so we thought about it. I would have loved to do it. Are you kidding me? It would have been great. But not at the cost of the most expensive investigation that rover carries.
Yeah, just a quick question about the power source. How long could the power source on Curiosity last? And are there any aspects of winter operations that impact Curiosity that in any way hamper the science being done through the winter?
Any aspect of what operations?
Winter operations.
Oh, okay. So first question about the power supply. It's the same plutonium power source that Voyager and Viking used. Voyager's doing just fine, 35 years, you know, after launch. And it has a half-life of 78 years or something. So power is going to be there. That's not going to be our limiting factor for decades. And that said, we are limited in winter time because the amount of power, while it's a steady source, is actually not that different than what was provided by the solar panels on Spirit and Opportunity when they were relatively clean. It's just constant, slowly decreasing with time. And so in the wintertime, it gets a lot colder, and we have to keep the inside of the vehicle warm, up -40 or some number like that, where electronics won't break, and that costs you power. And so the fraction of power that we have available to us every day is much higher in the winter that we have to spend on that heating and keeping the instruments alive. So it does limit us in drive duration and science operations.
Okay, here.
I had recently found out, just completely out of the blue, a game online called Take on Mars. Has anybody even heard of this? It's basically, it's a simulator of, you are NASA, you are building anything from a lander up to a Curiosity scale rover, and you design them, you customize them, you launch them, you land them, and then you run them by remote control and achieve science objectives. I think it's still like version 0.8, so I don't think it's in full release. But have you heard anything about this, and has there been any effort
Is it a NASA thing, or?
It's some other company, and they just did it on the fly, and it's actually, like I said, it's only version 0.8, so it's it's a little rough, but it isn't bad.
No, I haven't heard about it, and even if I had, I probably wouldn't have time to play the game because I'm doing the real thing.
It'd be too much like work, I think.
Thanks.
Okay, here.
If Curiosity lasts long enough, how far up Mount Sharp would you like to drive it, and how long do you think it would take?
Right. So there is a contingent of the science team that says, to the top! And that would be fun. But we don't need to go to the top. Those tilted layers that I showed you, that's pretty common from about 500 meters, half a kilometer up all the way to the top, which is another 4 kilometers or so. So if we can just get to the base of that tilted layer, then we'll pretty much know, based on orbital data, we think, we'll pretty much know what's the rest of the stack. And the rest of the stack is relatively new. It's the youngest stuff. It's on top. It's more recent in Mars history. It's more dusty, probably a little bit more oxidized. So we really want to get the juicy piece of the stratigraphy is that bottom 500 meters. And so, we're still at 0, so we need to go half a kilometer up. How long that will take depends on what that terrain is really like at the rover scale. We can see from orbit at the meters scale from the high-rise camera on MRO, and there are drive paths that have the right slopes that will allow us to get up there. We can go 20, 30 degree slopes if we need to. But we don't know in detail how slick the material is. Is it super sandy and we can't drive in it? Are there a lot of small rocks that are going to make driving very slow? We won't know till we get there, which is why we need to get there and find out. And we're trying.
What sort of narrowness of discrimination do you have on the laser spectroscopy on this? For instance, earlier today, we heard that on the grazing orbit that Nick Schneider's doing with LASP, he can discriminate deuterium from protium. I mean, dihydrogen from hydrogen. Yeah. And that takes an incredibly narrow line. Right. Now, I doubt it's here, but I think it's a good idea. You'd be able to tell if there was life having happened in carbon, for instance, if you could see what portion of it was carbon-14.
So 2 different questions there. One, we don't have the resolution in that spectrometer to measure isotopes at that scale. These are big, fat elemental lines like astronomers measure in emission nebulae and things like that, okay? And it's good resolution, but it's not that high. And secondly, I guess, I would debate the assertion that just by measuring the carbon isotope ratio, you can tell something about life, because there's plenty of other abiotic processes that can do isotope fractionation. So you'd need more than just one measurement. You'd need more than just one measurement to support that hypothesis, I believe. I don't remember. It's not my instrument. But there's papers been published. If you look up ChemCam, one word, ChemCam, and you'll find the papers that have been published with all those kind of beautiful details.
Okay, thank you, Dr. Bell.